So we've looked at integrals, single integrals, as a good representation of the area under a curve, okay? If we look at double integrals, we can think about it physically as the volume under some curve, right? So I'm going to set up a mathematical example, and then we'll look at a very simple physical system so you can see how the integration is related to volumes. Now, it doesn't have to be that because it will be related to a volume on a mathematical perspective, but your function can have different kind of physical representation. And we'll look at examples of when you would use double or triple integrals. Okay, so first we want to think about the concept of double integrals. We've already looked at the case where you have a single integral, right, and your upper and lower limits, and what you're integrating with respect to. When we have a double integral in this case, we're going to have two integral signs with two sets of upper and lower limits. And on the right side, you will have a dx and dy. You can have a variety of different variable forms, but you're going to have a representation of what you're integrating against. This is the same concept as when we're looking at partial derivatives, and we're looking at what are you taking the derivative of the function with respect to, right? So I'll put a link in the description to the partial derivative video if you want to review that first. You can think of the integral sign and the dx component as parentheses, right? So you have two integral signs here, and you have a dx and a dy component, right? So this inner integral right here, related to x limits, is associated with this inner dx term here. This outer integral sign here, associated to the y values, y limits, is associated to the dy values here. So you start, when you do the integration, you start from the most inner values, you integrate that, you apply your limits, and then you go to your outer limits, or your outer integral. Okay, so we're going to just do it for double integrals, but the same concept applies if you have triple, quadruple, or any higher order number of integrals. So we're going to do two examples to show how this is done. All right, so for this first example, we need a example function and limits a, b, and c, d associated with your x and y limits to solve this example problem. So I randomly picked this function. It's a function of x and y, so we can apply it directly to this double integral, right? And I also randomly picked some upper and lower limits here, right? So remember, the upper limit y equals 6, y equals 3 is associated with this dy. That's the outer integral, right? So that's going to be the second integral we do. We're going to start with the integral, the inner integral right here, this dx, x equals 3 is my upper limit, x equals 1 is my lower limit. So I take our function, plug it in here, and we focus on this integral, right? Just like in partial derivatives, when we take this integral, we ignore the variable that is not associated. So this right here tells me what variable I need to take this integral with respect to. I'll take it with respect to x. That means this y term is going to be looked at as a constant, so I can completely ignore it. So when I integrate yx cubed with respect to x, well, first of all, I can separate these two terms, this x cubed y and 2x squared, using the fact that I know from a previous video that integral of a function subtracted by another function can be just separated as the integral of each one individually subtracted, right? So we can do that still here as well. So x cubed times y is my constant because I'm taking this integral, this first integral with respect to x. So I need to take the integral of x cubed. I look over at my table and it'll be this form right here. So this will be 1 over 4 x to the fourth times y, because y would be looked at as a constant. So then you can use this principle as well. The second term here, minus 2x squared. let's see. So 2 would be my constant. X squared. We'll look here again. The integral of x squared with respect to x is going to give me 1/3 x cubed. And so that solution will be here. And then I would need to apply the upper and lower limits of the x component, right? So x cubed integral is x to the 4th over 4. Y is my constant that I need to keep right there. The integral of x squared, like we said earlier, was 1 over 3 x cubed. That's right here, multiplied by my constant 2. Okay, so I need to apply my upper and lower limits, x equals 3 and x equals 1. And then I would solve my second integral. So let's apply the upper and lower limits. Remember, you apply the upper limit by plugging in here, and subtract that by applying the lower limit to this function. So I'll plug in 3 wherever you see x, so it'll be 3 to the 4th power over 4y minus 2/3 3 cubed. That's my upper limit, minus my lower limits, 1 to the 4th power over 4y minus 2/3 1 cubed. Okay, so we can simplify this, and then we'll solve the second integral. So we simplify this, we'll combine the y terms here. So 3 to the 4th is 81 over 4. Y minus 1 over 4y, it'll be just 80 over 4y. Or we could simplify it further as 20y. Over here we have negative 2/3 3 cubed. 3 cubed is 27. Over here we have minus negative 2/3 1 cubed, which is just 1 cubed is 1. 27 and 1 will give me 26. So negative 2/3 20 times 26. Right, you can further simplify it before if you like, right, with them. But now this is just like what we've done in the past. We integrate this component here. So we integrate this with respect to y. There are no x terms anymore because we already applied the first upper limit components. So this is 20. 20y, integral of that is y squared over 2. So 20y squared over 2 minus 26 times 2 is 52. 52 over 3. So that's a constant. So the integral of a constant with respect to y would be that constant times y. That's what we have here. And then we apply the y limits. Upper limit of 6, lower limit of 3, just like we've done in the past. So you plug in 6, and then you subtract that by after you plug in the 3, right? So 10, 20 over 2 is 10. 10 times 6 squared minus 52 over 3 times 6. That's my upper limit component, minus 10 times the lower limit squared, 3 squared, minus 52 over 3 times y, or my lower limit 3. And you simplify this, and you get your solution 280 in this case, right? So let's walk through the steps again. You solve for your inner limit first. Once you apply you solve for your inner integral. Once you apply your upper and lower limits, like you do here, then you solve for your next integral. If there was a triple integral, you apply this, and then you'll solve it for the third integral. Maybe there's a z term, and that will linger there too. All right, so let's take a look at another example where we can see a physical representation of this double integral. They give it a little bit more meat of what do these double integrals actually look like? All right, so we're going to do things a little bit different in this example. I'm actually not going to use x and y. I'm going to use x and theta. And we'll see in a second why I'm choosing to switch it up just for the sake of this example. Let's say my function f is actually just y equals 4. Just a constant horizontal line, y equals 4. Right? And I'm going to take two integrals. My goal is to solve for a volume. I want you to see how a double integral can be associated with a volume. So the volume I'm going to look at is going to first integrate this y value from x equals 0 to x equals 2. Then I'm going to integrate across theta. And theta is kind of using the y-axis as my axis of rotation. So it's going to rotate around it. and it's going to rotate a full revolution from 0 to 2 pi, right? 0 to 360 degrees. And I want you to see if you can predict what kind of shape you actually get, because I'm defining this as my volume. So I want to graphically show what this looks like, right? So remember, integral, right? If we just focus on that first integral, integral is just area under the curve. So it goes from the function and the area from that function or that line to the x-axis. So if I'm taking the integral from 0 to 2, I only need to focus on x equals 0 to x equals 2, right? So this range. And then I'm going to integrate. So this is going to be my area under this curve, which is easy because that's just a rectangle, right? So if I take that integral of 4 dx, that's just a constant. So it's going to be 4x. And then we apply our upper and lower limits of x equals 2 and x equals 0. So we can do that, apply x equals 2 minus x equals 0, right? So you could write this as 4 times 2 minus 4 times 0. Anyway, either way, you will get your integral will be equal to 8. What does that actually represent? That represents this area, the area of this rectangle, right? So the area underneath the y equals 4 from the limits 0, x equals 0 to x equals 2. Okay. Straightforward enough. Now I have a d theta. What is this d theta representing? Well, I said theta, I'm defining it as coming out of the board, just basically circling around. I'm defining this range, this limit from 0 to 2 pi, right? Going from one location, rotating all the way around. So full revolution. I could change this if I want, and I'll define a different kind of shape. But I want to define that full shape right there, right? Okay, so you can think about this from a physical perspective, and you can also think about this from a mathematical perspective. So connecting the two concepts that's our goal right now. So I'm going to rotate around the y-axis. If I integrate this, just look at theta as a y value or x value. It doesn't really matter. It's a dummy variable for the sake of what we're looking at it as, right? So 8 is a constant. So just like what we had earlier, this will be 8 theta. Right, the integral of it. Where do we got that? Right here, right? Then I need to apply my upper and lower limits. Theta equals 2 pi, so 8 times 2 pi minus 8 times 0. So it's just 8 times 2 pi, or 16 pi. That's what we say is the volume of whatever shape, right? What shape would you actually get if you rotated a rectangle about one of its sides? That's essentially what we're doing right here, right? So I rotated about one of the sides, I get a cylinder. Well, from a previous video, we also know how to solve for the volume of a cylinder. How do you solve for the volume of a cylinder? You can solve for the area of this top circle, and then you multiply it by the height of this, right? So the radius of this circle, how do I know this? Well, it's just this distance right here, right? Because I'm rotating across. So what's this distance? This is the limit, the upper limit of x. So that would be 2, right? So r equals 2. What's the height of this cylinder? Well, that's the function y value. In this case, it's equal to 4. So if I look for the volume, pi r squared times h, r squared is 4, h is 4, so 4 times 4 is 16, 16 pi. So the volume is 16 pi. So it's consistent there. So you can see that you can change the shape here, and you can have a different rotation. You can change the limits. You can have a hollow cylinder. So you can use a double integral to do something very simple in mathematically, but might be very complex in a geometry sense. And we'll see. We'll take a look at a lot of physical systems that uses multiple integrals to solve things beyond just geometry.